Right now, Earth is sitting inside a bubble of space, roughly 2 billion light-years across, where matter is measurably thinner than it should be. This is not a theory or a model artifact. Astronomers confirmed it in 2013 after mapping the positions of 35,000 galaxies and finding a consistent, persistent 20% deficit of matter in every direction they looked. The region has a name, the KBC Void, named after the 3 astronomers who identified it: Ryan Keenan, Amy Barger, and Lenox Cowie. Most people have never heard of it, but the KBC Void may be responsible for one of the most significant crises in modern cosmology. It may be biasing every local measurement of how fast the universe expands, and its very existence sits at the edge of what standard physics says should be statistically possible. This is a story about where we are, how we figured that out, and what it means. When Keenan, Barger, and Cowie began their galaxy survey, they were not looking for a void. They were trying to build a more accurate picture of the large-scale structure around us, cataloging which galaxies exist, where they sit, and how their densities compare to what cosmological models predict. What they found was a systematic shortfall. Compared to theoretical predictions for what the galaxy count should look like within a billion light-years in every direction, the actual number was about 20% lower. The deficit was not concentrated in one patch of sky. It was spread uniformly outward in all directions, forming an enormous sphere of underdensity with the Milky Way sitting somewhere near its interior. The researchers checked their data against multiple independent galaxy surveys. They approached the sky from different angles. The answer remained consistent. We are inside an underdense bubble of space so vast that it dwarfs every previously identified void structure on record. This finding placed Earth, along with its galaxy group, and the entire supercluster that contains all of those within one of the most extreme low-density environments ever observed. At first glance, a void might seem like a minor curiosity of large-scale structure. Space is full of voids between galaxy filaments. That is expected. But the KBC Void is not the ordinary emptiness between galaxy clusters. Its scale, its depth, and its apparent statistical rarity are what make it significant. And as scientists began working through the implications, they found it connects to a problem that was already keeping cosmologists up at night: the Hubble tension. The Hubble constant is one of the most fundamental numbers in cosmology. It tells us how fast the universe is expanding, specifically how many kilometers per second a galaxy recedes from us for every megaparsec of distance between us. 1 megaparsec is about 3.26 million light-years. There are 2 main ways to measure this number, and they give different answers. The first method works backward, from the cosmic microwave background, the faint glow of thermal radiation left over from when the universe was about 380,000 years old. By feeding the detailed temperature patterns of this ancient light into cosmological models, scientists can calculate what the expansion rate must have been in the early universe, and from there, what it should be today. This approach consistently returns a value of around 67 kilometers per second per megaparsec. The second method builds a distance ladder using nearby objects with known intrinsic brightness, type Ia supernovae and Cepheid variable stars, whose pulsation rates correlate precisely with their luminosity. By comparing how bright these objects appear versus how bright they actually are, astronomers calculate their distance. Combine distance with redshift measurements, and you get the local expansion rate directly. This method consistently returns about 73 kilometers per second per megaparsec. That gap, 67 versus 73, represents a 9% discrepancy. Both measurements are precise enough that random error cannot explain it. Both have been independently verified by multiple research teams using different instruments and different techniques. The discrepancy has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. This is known as the Hubble tension, and it is one of the most debated problems in modern physics. Here is where the KBC Void enters the picture. When the local Hubble constant is measured using supernovae, those supernovae are sitting inside the same void we inhabit. The void's low matter density changes the local gravitational landscape. All of the mass that is missing from the void, the 20% deficit, is concentrated in the denser filaments and walls surrounding it. The gravitational pull of that exterior matter tugs on galaxies within the void, accelerating them outward. They are not just receding because space is expanding, they are also being pulled outward by the gravitational imbalance created by the void geometry. This adds extra velocity to galaxies within the void. When we measure their recession speed and convert it to an expansion rate, we get a number that is inflated above the true global average. The void is effectively giving galaxies within it an additional outward kick that mimics a faster expansion. Calculations show that a void of the KBC's scale, roughly 1 billion light-years in radius, with a 20% density deficit, can produce precisely the boost needed to explain the observed discrepancy. This does not necessarily mean scientists made errors. It means the measurement is accurate, but the location from which it was made introduces a systematic bias. We are not measuring the universe's expansion rate. We are measuring the expansion rate as seen from inside a gravitational anomaly that amplifies the apparent value. To understand what it means to be inside the KBC void, it helps to have a clear picture of our position within it and within the broader cosmic hierarchy. The Milky Way is one of about 80 galaxies that form the local group. The local group spans a few million light-years and includes Andromeda, the Magellanic Clouds, and dozens of smaller dwarf galaxies. The local group is itself part of a much larger structure called the Laniakea supercluster, identified in 2014 by mapping the velocity flows of galaxies across our region of the universe. Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and roughly translates to immeasurable heaven. The structure is defined not by proximity alone, but by gravitational flow patterns. All the galaxies within Laniakea are flowing toward a common gravitational center called the Great Attractor. The Milky Way sits on the outer edge of Laniakea, and we are gravitationally bound to it. Our peculiar velocity, the motion of our galaxy, beyond what cosmic expansion explains, is partly directed toward the Great Attractor. Here's what is remarkable about this. Even Laniakea, an enormous supercluster containing 100,000 galaxies spanning over 500 million light-years, sits entirely inside the KBC void. The KBC void is so vast that a structure of Laniakea's scale barely registers as a perturbation within it. Our position within the void is not at its center. Measurements suggest the Milky Way is roughly 200 to 400 million light-years from the true center of the void, but the void extends about 1 billion light-years in every direction from that center. We are well inside it, surrounded by the void's low-density environment in all directions. Beyond the void's edge lies a shell of higher-density structure, filaments, and clusters, where the density rises back toward the cosmic average. When astronomers look outward from Earth through their telescopes, they see this shell as a concentration of galaxy clusters at a specific distance range. It is the wall of the void. Beyond that wall, the universe returns to something closer to normal density. In addition to the large KBC void, we are also adjacent to a smaller but distinct structure called the local void, which spans about 200 million light-years. Our galaxy is actively flowing away from the local void at around 260 kilometers per second as part of a broader outflow pattern called the local sheet, a flattened arrangement of galaxies that includes the Milky Way, Andromeda, which is rushing away from the local void's center. Adding all these gravitational effects together, the pull toward the Great Attractor, the outflow from the local void, the gravitational influence of the Virgo cluster about 60 million light-years away, and the future merger trajectory with Andromeda, gives the Milky Way a total peculiar velocity of roughly 627 kilometers per second relative to the cosmic microwave background rest frame. That figure corresponds directly to a temperature dipole observed in the cosmic microwave background, and it is consistent with what you would expect from a galaxy sitting inside a large underdense region. We are not stationary. We are moving fast, and the void is a significant reason why. Voids are the dominant structural feature of the universe by volume. Roughly 90% of the total volume of space is void. The filaments, walls, and clusters of galaxies that we tend to focus on occupy only the remaining 10% of the volume, but they contain most of the mass. This distribution emerged from the earliest moments of cosmic history. In the first fraction of a second after the Big Bang, during a period called cosmic inflation, the universe expanded exponentially, and quantum fluctuations at subatomic scales were stretched to cosmic scales. These fluctuations imprinted tiny variations in density, some regions denser by perhaps 1 part in 100,000, others slightly less dense. Those differences seem negligible, but gravity amplifies them over time. Denser regions attracted more matter from their surroundings, becoming denser still. Less dense regions lost matter to their neighbors, growing emptier. Over hundreds of millions of years, this process built the architecture we observe today, a cosmic web of filaments and sheets surrounding vast hollow regions. The voids are not truly empty. They contain dark matter, just at much lower concentrations than average roughly 15% of the cosmic average density. They contain dark energy, which is uniformly distributed throughout space and is therefore present in voids at the same density as everywhere else. They contain occasional wisps of hydrogen gas and the rare isolated galaxy, but they lack the gravity to build new structure. Without sufficient mass, gravity cannot pull matter into clusters or form new filaments. The void stays a void. This is where dark energy becomes important. In dense regions, gravity and dark energy compete. Gravity pulls matter together, while dark energy pushes space apart. The two forces partially cancel, and the expansion of dense regions is slower than the cosmic average. Inside voids, this competition does not exist. With so little matter, gravity contributes almost nothing. Dark energy dominates, and voids expand faster than the rest of the universe. This creates a self-amplifying dynamic. The faster a void expands, the emptier it becomes, which reduces the gravitational resistance to further expansion. Voids grow like bubbles, pushing outward and compressing the surrounding filaments into denser, thinner walls. The effect has a measurable signature. Astronomers have observed that galaxies near void edges move outward faster than expansion alone would predict. The velocity surplus matches what you would expect from the gravitational pull of the denser matter, outside the void acting on the interior. The physics is geometric. Think of the void as a low-density valley surrounded by high-density ridges. In gravitational terms, there is more mass pulling galaxies toward the ridges than toward the center. The net effect is an outward flow from the void's interior. This same physics applies to the KBC Void and produces our galaxy's unusual speed. The surplus motion is detectable. It is consistent with the void's measured properties, and it directly affects every nearby measurement of cosmic expansion. The existence of the KBC Void would be interesting regardless of its size, but what makes it scientifically explosive is that it should not exist, or at least should be extraordinarily rare. The standard cosmological model, known as lambda-cold dark matter, or LCDM, has been remarkably successful at explaining the large-scale structure of the universe. It predicts how structures grow from the initial density fluctuations left by inflation, accounts for the observed temperature patterns in the cosmic microwave background, explains the abundance of light elements produced in the Big Bang, and correctly describes the general appearance of the cosmic web. One of its key predictions is the statistical distribution of void sizes. Small voids, tens of millions of light years across, should be common because they form from common small-scale fluctuations. Medium voids should be less common. Extremely large, deep voids should be very rare because they require very large initial underdensities that are statistically improbable given the smoothness of the early universe. When researchers run computer simulations of structure formation using standard parameters and look for voids comparable to the KBC Void, roughly 2 billion light-years across, with a 20% density deficit, they find almost none. Some analyses estimate the probability of such a void occurring in the observable universe at roughly 1 inch 1,000. Others have calculated that the KBC Void represents a 1-0 sigma deviation from expected density, meaning you would need to survey trillions of universe-sized volumes before expecting to find a single such structure by chance. To put that in context, a 5 sigma result is already considered practically impossible in physics and is the standard threshold for claiming a discovery. A 10 sigma result is incomprehensibly more improbable. Yet we live in one. This creates an immediate logical tension. Either the standard cosmological model is missing something important about how large structures form, or we happen to occupy an extraordinarily unusual position in the universe. Neither answer is satisfying from a scientific standpoint. Critics of the standard model use the KBC Void, along with other large-scale anomalies like the Shapley supercluster and the Sloan Great Wall, as evidence that structure formation in the real universe is more vigorous than the model predicts. Something may be missing from LCDM that would allow larger, deeper voids and richer clusters to form without requiring rare initial conditions. Defenders of the standard model note that the cosmos is large enough that even improbable events can occur somewhere, and that nearly every other prediction of LCDM has been confirmed with high precision. They argue that abandoning a successful theoretical framework based on one anomalous structure is premature, especially when measurement uncertainties about the void's exact depth and extent remain. A third position holds that the void may not be as extreme as the initial measurements suggested. Different observational techniques have produced density deficits ranging from about 10% to 20%. If the true deficit is closer to the lower end, the statistical rarity becomes less severe. Confirming the void's exact properties requires deeper galaxy surveys, with better completeness surveys that will be delivered by upcoming missions. The statistical difficulty of explaining the KBC void within standard cosmology has motivated several researchers to consider whether the physics of gravity or structure formation needs modification. One of the oldest alternative gravity theories is modified Newtonian dynamics, or MOND. Originally proposed to explain why galaxies rotate faster at their edges than standard gravity predicts without dark matter, MOND adjusts the force law at low accelerations. When applied to cosmological structure formation, MOND produces more vigorous clustering, denser clusters, and deeper voids compared to standard Newtonian gravity with cold dark matter. Computer simulations using MOND gravity naturally generate voids with the scale and depth of the KBC void without requiring unusual initial conditions. The statistical improbability disappears. However, MOND faces serious difficulties beyond galaxy rotation curves. It struggles to explain gravitational lensing observations in galaxy clusters, where the observed bending of light requires more mass than MOND's enhancement of visible matter can supply. It also does not reproduce the fine-scale temperature patterns in the cosmic microwave background as accurately as the standard model. Some hybrid theories combine MOND with small amounts of dark matter, often in the form of massive neutrinos, to address these problems. But these models introduce their own complications. A broader class of modified gravity theories adjusts the behavior of gravity on cosmological scales without changing its predictions on smaller, well-tested scales. Some of these theories introduce additional fields, or higher dimensional effects, that effectively make gravity stronger in low-density environments like voids. If gravity is enhanced in voids, those regions would drain their matter faster and reach greater depths, making large supervoids more probable. Testing whether gravity deviates from general relativity in void environments is now a major goal of observational cosmology. The discriminating evidence will come from precise measurements of how matter flows in and around voids. If the velocity patterns of galaxies near void edges deviate from general relativity's predictions, if matter flows faster or slower than expected, that would indicate modified gravity at work. Current measurements are consistent with general relativity, but are not yet precise enough to rule out modest modifications. Another approach focuses not on modifying gravity, but on the initial conditions left by inflation. Standard inflationary models predict a nearly scale-invariant spectrum of density fluctuations, meaning all scales contribute approximately equally to the initial density contrast. Some modifications to inflation can produce extra power on large scales, meaning bigger fluctuations at the scale of supervoids. If the inflationary spectrum had slightly more power at scales corresponding to billions of light years, large voids would form more easily, and the KBC void's existence would be less improbable. Distinguishing between these possibilities requires mapping the universe on very large scales to determine whether structures comparable to the KBC void are truly rare or are simply the high end of a broader distribution that the standard model underestimates. Underlying all of these debates is a foundational assumption in modern physics called the cosmological principle. It states that the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, when averaged over sufficiently large scales. No location is special, no direction is preferred. This principle is not just a philosophical preference. It is a mathematical convenience that makes the equations of general relativity tractable for describing the universe as a whole. Without it, cosmological models become vastly more complicated. With it, a few simple parameters describe the entire history and structure of the cosmos. The cosmological principle has been remarkably productive. It underpins the standard Big Bang model, the predictions of the cosmic microwave background, and the standard model of cosmology. Its success in explaining observations has reinforced the assumption that it is correct. But the KBC void creates friction with this principle. A structure 2 billion light-years across, with a 20% density deviation, is a significant inhomogeneity. It is large enough to represent a meaningful fraction of the observable universe's volume, and we are near its center. The uncomfortable implication is that our location may not be typical. Science has made a long historical trend of removing Earth from any special position. Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. The cosmological principle is the final step in that progression. Not only are we not at the center, but there is no center, because all positions are equivalent. The KBC void, if it is as extreme as the most detailed measurements suggest, implies that Earth does occupy an unusual position inside one of the largest known underdensities in the observable universe. That does not put us at the center of anything, but it does mean our location is statistically far from ordinary. Some cosmologists argue that the homogeneity requirement only applies at scales larger than the void, that the cosmological principle is still valid at scales of several billion light-years. And the KBC void is simply a feature of the messy intermediate scale where structure has not fully averaged out. Others use the anthropic principle to argue that observers preferentially form in mildly underdense regions where galaxy formation is favorable. So, finding ourselves in a moderate void is not surprising. These arguments are contested. A 20% deficit is not mild. The debate matters not just philosophically, but observationally. If the cosmological principle does not hold at the scale of the KBC void, then measurements made from our location, including every local measurement of the Hubble constant, are systematically influenced by our unusual vantage point. We may be trying to infer universal properties from a position that does not sample the universe fairly. Future sky surveys will test this directly. If large voids are more common than standard cosmology predicts, the principle survives, but the model needs revision. If they are as rare as simulations suggest, we face the harder question of why we happen to be in one. Cosmic voids have an unusual scientific value that extends beyond their challenge to standard models. They are the best natural laboratories in the universe for studying dark energy. Dark energy was discovered in 1998 through observations of distant type Ia supernovae. Astronomers expected to find that the expansion of the universe was slowing down, that gravity would be pulling matter back together and decelerating the expansion over time. Instead, the supernovae appeared fainter than expected, indicating they were farther away than a decelerating universe would place them. The expansion was accelerating, not slowing. Some energy component was pushing space apart. This component was called dark energy. Dark energy now accounts for about 68% of the total energy content of the universe, according to the standard model. Unlike matter or radiation, it does not dilute as the universe expands. Its density appears to remain constant, even as space itself grows. This gives it an ever-increasing share of the cosmic energy budget and a growing influence on cosmic dynamics. Despite its dominance in the cosmic energy budget, the nature of dark energy remains unknown. The simplest interpretation is that it is a cosmological constant, an intrinsic energy density of empty space, constant throughout time and uniform across all locations. Albert Einstein introduced this concept in his field equations, though he later considered it an error. The modern revival of the cosmological constant has it serving as the driver of cosmic acceleration. But this is not the only possibility. Dark energy could be a dynamic field that varies in strength with time or space. If it was weaker in the past and stronger now, expansion would have accelerated differently over cosmic history. If it varies across locations, it would affect structure formation differently in different environments. Distinguishing between a constant and a dynamic dark energy requires precise measurements of how expansion has behaved at different cosmic epochs and in different environments. This is where voids become indispensable. In dense regions, gravity and dark energy compete. The expansion in and around galaxy clusters is slowed by the gravitational pull of all that mass. Disentangling the dark energy signal from the gravitational noise is difficult. In voids, matter is scarce, and gravity is negligible. Dark energy operates almost unimpeded. The expansion of voids is essentially a direct measurement of dark energy's repulsive influence. By measuring how fast voids expand, how quickly their edges push outward, and comparing that to predictions based on different dark energy models, scientists can constrain dark energy's properties. If dark energy is a cosmological constant, voids should expand at a rate that matches the standard model precisely. If dark energy evolves or varies, the expansion rates will deviate. Void shapes provide a complementary test. If dark energy is perfectly uniform, voids should expand equally in all directions, maintaining roughly spherical shapes. If dark energy has spatial structure, or if there are unknown forces, voids might expand differently along different axes, becoming elongated or compressed. Observing the statistical shapes of many voids allows tests of dark energy uniformity. Current surveys show most large voids are approximately spherical, consistent with uniform dark energy, but the precision is not yet sufficient to rule out modest variations. The KBC void, being both the largest known nearby supervoid and the one we can study in most detail, is particularly valuable for these measurements. Its proximity allows mapping of internal structure and velocity fields at a resolution impossible for distant voids. As galaxy surveys improve, measurements of the KBC void's expansion rate and shape will constrain dark energy properties far better than current data allow. The low-density environment of a void does not just affect large-scale cosmology, it shapes the formation and evolution of the galaxies that develop within it. Galaxies inside voids grow up in relative isolation. Unlike galaxies in dense clusters, which frequently interact with neighbors colliding, merging, stripping gas from each other, and feeding material into each other's central black holes, void galaxies evolve with minimal external interference. This environmental difference produces distinctive characteristics. Void galaxies tend to be smaller and less massive than their counterparts in filaments and clusters. Many qualify as dwarf galaxies, barely large enough to hold onto their gas against the outward pressure generated by star formation. Without the mass to anchor their gas, and the gravitational encounters to fuel growth, they remain relatively modest structures. Mergers are a key driver of galaxy evolution in dense environments. When two galaxies collide and combine, the gravitational disruption compresses gas clouds and triggers intense bursts of star formation. Merger-driven star formation is responsible for many of the most massive and luminous galaxies we observe in rich clusters. It also feeds material into supermassive black holes, making them grow and sometimes activating quasars' enormously luminous episodes of black hole accretion that can outshine entire galaxies. In voids, this process is largely absent. Galaxies evolve on their own internal dynamics. Their star formation rates are generally lower, and their growth is gradual. They retain disk structures and spiral arms that would be disrupted by mergers in denser environments. There is a surprising twist, however. While most void galaxies are quiescent, a disproportionate fraction of them undergo brief, intense episodes of star formation, called starbursts. This seems paradoxical until you consider the gas reservoir. In dense environments, galaxies continuously lose gas through interactions with neighbors. Tidal forces strip material from their outer disks. The hot diffuse gas-filling galaxy clusters, the intracluster medium, can also ram pressure strip gas from infalling galaxies. Void galaxies avoid these processes. They retain their neutral hydrogen for longer, building up large reservoirs of unprocessed gas. When something internal to a void galaxy eventually triggers star formation, perhaps a minor internal gravitational instability, there is an abundance of fuel available. The result is a brief but intense starburst that consumes a large fraction of the gas reservoir before the galaxy settles back into relative inactivity. This pattern, long quiescence followed by intense brief episodes, is distinct from the continuous moderate star formation seen in typical cluster galaxies, and it reflects the unique environmental history of void galaxies. The chemical composition of void galaxies also differs. Stars create heavy elements through nuclear fusion and disperse them into the galaxy's gas when they die in supernovae. Later generations of stars form from this enriched gas, and the galaxy's overall metallicity, the abundance of elements heavier than helium, gradually increases over time. This process is slower in void galaxies because they form stars at lower rates. Void galaxies tend to have lower metallicities than galaxies in dense regions, though the difference is smaller than naive models predict, suggesting that gas exchange with the surrounding intergalactic medium plays a role in chemical evolution. The dark matter halos surrounding void galaxies are also structurally distinct. Dark matter halos and clusters are continuously disturbed by tidal forces from neighboring halos. They become elongated, compressed, and misaligned with the galaxies they contain. Void galaxy halos are less disturbed. They remain more spherical and better aligned with their galaxies. This simpler structure makes void galaxy halos easier to model and provides cleaner tests of dark matter behavior. One limit defines where galaxies can form at all in voids. Below a certain halo mass, corresponding to a circular velocity of roughly 35 kilometers per second, the gravitational well is too shallow to efficiently retain gas through the cycle of cooling, collapse, and star formation. Halos below this threshold may exist in voids, but remain dark, containing dark matter, but no visible stars, no galaxies. This explains why voids are not uniformly filled with tiny, faint dwarf galaxies. At some scale, the environment is simply too empty for galaxies to assemble. The KBC Void does not merely challenge the measurement of expansion. It puts pressure on one of cosmology's most fundamental parameters, the age of the universe. The current best estimate for the universe's age is 13.8 billion years. This comes from detailed modeling of the cosmic microwave background, combined with the standard cosmological parameters, the matter density, the dark energy density, and the expansion rate derived from early universe measurements. If the local Hubble constant measurement of 73 kilometers per second per megaparsec reflects the true global expansion rate, rather than a void-inflated local value, the universe has been expanding faster throughout its entire history. A faster expansion rate means the universe reached its current size in less time. Calculations show this would imply a universe about 12.7 billion years old, roughly 8% younger than the current estimate. This creates a concrete problem. The oldest stars, in globular clusters, spherical collections of hundreds of thousands of stars that formed together in the early universe, appear to be about 13 billion years old, based on stellar evolution theory. The dating method is straightforward in principle. Stars of different masses burn through their nuclear fuel at different rates. By observing which stars in a cluster have just barely reached the end of their main sequence lives, astronomers can estimate when all the stars in that cluster formed. You cannot have stars that formed before the universe existed. A 12.7 billion year old universe with 13 billion year old stars is self-contradictory. Various ways out have been proposed. Perhaps stellar models are systematically wrong in their treatment of how stars burn hydrogen or how they evolve off the main sequence, which could shift age estimates by hundreds of millions of years in the right direction. But stellar physics is well constrained by observations from multiple angles, and requiring a systematic error large enough to resolve the contradiction demands specific and implausible assumptions. White dwarf cooling times provide an independent age constraint that does not depend on stellar evolution models. White dwarfs, the remnant cores of dead stars, cool gradually and predictably as they radiate stored heat into space. The coolest white dwarfs we have found have been cooling for approximately 12 to 13 billion years. This independently confirms a universe older than 12.7 billion years. The cleanest resolution comes from accepting the void explanation for the local Hubble constant excess. If the 73 kilometers per second measurement is inflated by our position inside the KBC void, then it does not represent the universe's global expansion rate. The cosmic microwave background measurement of 67 kilometers per second per megaparsec applies to the early universe and to the global average, and the derived age of 13.8 billion years remains valid. The apparent discrepancy between local and early universe measurements is not evidence that the universe is younger. It is evidence that our local neighborhood is unusual. This resolution preserves the age of the universe and removes the contradiction with stellar ages. But it requires accepting that every precision measurement made locally over the last few decades has been systematically biased by our position inside an extraordinarily large cosmic void. The questions raised by the KBC void will not remain unanswered for long. A new generation of astronomical surveys is already underway or in preparation, designed with the precision to resolve the key uncertainties. The Euclid Space Telescope, launched in 2023 and beginning full science operations in 2024, will map the positions and shapes of billions of galaxies across a large fraction of the sky and out to distances of many billions of light years. Its primary scientific goals include measuring the expansion history of the universe and the growth rate of large-scale structure. These measurements will directly test whether the dark energy driving cosmic acceleration behaves like a cosmological constant or like a dynamic field that evolves. Euclid will also discover and catalog thousands of voids at different distances and sizes, providing the statistical sample needed to determine how rare supervoids, like the KBC void, truly are. The Vera Rubin Observatory in Chile, when it reaches full operational capacity, will conduct the Legacy Survey of Space and Time, a decade-long photometric survey that will observe approximately 20 billion galaxies over the southern sky. This survey will map the three-dimensional distribution of matter to greater depth and completeness than any previous instrument, providing the most detailed picture of the cosmic web yet assembled. It will also discover supernovae at a rate of roughly 10,000 per year, improving the local Hubble constant measurement with unprecedented statistical power. If the KBC void's influence on these measurements is real, the pattern should become unmistakable in Vera Rubin's data. The dark energy spectroscopic instrument, known as DESI, is already operating and mapping galaxy spectra at a rate of millions per year. Its goal is to measure the Hubble constant, the growth of structure, and the equation of state of dark energy through baryon acoustic oscillation measurements, using the characteristic spacing of galaxy clustering as a cosmic ruler. DESI results are expected to significantly tighten constraints on all of these parameters and to map the velocity field around the KBC void in unprecedented detail. The Square Kilometre Array, currently under construction in South Africa and Australia, will survey neutral hydrogen across the universe at radio wavelengths. Neutral hydrogen is the raw material of star formation and traces the distribution of matter in ways optical surveys cannot. The SKA will map void interiors, characterize void galaxies across cosmic time, and measure how gas content evolves in low-density environments. It'll test the predictions of standard and modified gravity theories about how matter flows in and around voids. Together, these instruments represent an extraordinary leap in observational capability. The key measurements they will enable fall into several categories. First, they will constrain the Hubble tension by dramatically improving the precision of both local and early universe expansion rate measurements and determining whether the gap between them persists as systematic errors are eliminated. Second, they will map the three-dimensional density field of our region with sufficient detail to confirm or revise the current estimates of the KBC Void's depth and extent. Third, they will measure the statistical distribution of large voids across the observable universe, establishing whether the KBC Void is genuinely a rare outlier or whether standard cosmology simply underestimates how common large underdensities are. If the new surveys confirm that the KBC Void is as large and as deep as current measurements suggest, and if similar structures are found to be exceedingly rare, the pressure on the standard cosmological model will intensify dramatically. Modified gravity theories, or modifications to inflationary models, will need to be taken more seriously. If instead the surveys reveal that large voids are more common than simulations currently predict, it may indicate that structure formation in the real universe is slightly more vigorous than LCDM assumes, a more modest revision that preserves the overall framework while adjusting its parameters. Either outcome advances our understanding significantly. The void's existence has already forced cosmologists to examine assumptions that had been taken for granted. The upcoming wave of observational data will determine whether those assumptions need to be abandoned or simply refined. The void we inhabit is not a static feature. It is part of a dynamic structure that has been evolving since the universe began and will continue evolving as long as the universe exists. In the early universe, the cosmic web was just beginning to assemble. The first stars ignited in dense knots of hydrogen about 100 to 200 million years after the Big Bang. The first galaxies assembled over the following hundreds of millions of years. The filaments connecting these galaxies and the voids separating them were smaller and less pronounced. The structure was there, but density contrasts between voids and filaments were smaller than today. Over the past 13 billion years, gravity has been working continuously. Dense regions have drawn in more and more matter, growing richer. Voids have emptied progressively, losing matter to the surrounding filaments. The cosmic web has become increasingly pronounced over time, with higher density contrasts between voids and clusters. Dark energy adds a complicating factor. For the first several billion years of cosmic history, matter dominated the energy budget and gravity determined how structures evolved. But as the universe expanded, the density of matter, which thins out as space grows, fell while the density of dark energy remained approximately constant. About 5 billion years ago, dark energy became the dominant component. Since then, the accelerating expansion it drives has been competing with gravity. In this dark energy-dominated phase, the growth of structure has slowed. Voids are still expanding, but the rate of new cluster formation has decreased. Matter that was flowing toward filaments and clusters in the matter-dominated era is now being stretched by the accelerating expansion before it can fully collapse. In the far future, this process will continue. The Milky Way and Andromeda will collide and merge in roughly 4 billion years, forming a new combined galaxy, sometimes called Milkomeda or Milkdromeda. This merged structure will be the dominant object in the local group, but the local group itself will become increasingly isolated as the accelerating expansion pushes other nearby groups beyond our cosmic horizon over tens of billions of years. As cosmic expansion accelerates, galaxies beyond a certain distance will recede faster than light can bridge the gap. They will effectively disappear from the observable universe. The local group will find itself in an expanding void of its own, cosmically isolated, even if not locally lonely. Over trillions of years, star formation will gradually cease as gas is consumed or expelled from galaxies. The Milky Way, or its descendant, will slowly dim as aging stars exhaust their fuel and younger stars become rarer. The night sky will darken over geological timescales as the stellar population ages. Over even longer timescales, tens to hundreds of trillions of years, the last stars will exhaust their nuclear fuel. Galaxies will consist of stellar remnants, white dwarfs gradually cooling toward invisibility, neutron stars, and black holes. Eventually, gravitational interactions between these remnants will scatter most of them out of galaxies entirely, leaving isolated objects drifting through an expanding void. Black holes will remain as the last major structural features. Through a quantum mechanical process described by Stephen Hawking, black holes slowly evaporate by radiating energy over incomprehensibly long timescales. A stellar mass black hole would take roughly 10 to the 67th years to evaporate. Supermassive black holes would take far longer, but eventually, even they would disappear. What remains is a diffuse, cold, expanding sea of particles and radiation. The voids that are a notable feature of today's universe will become everything. The filaments and clusters we see as the defining structures of the cosmic web are a transient phase, impressive on human timescales, but ephemeral in the context of cosmic time. The universe's long-term destiny, given what we understand about dark energy, is progressive emptiness. The void we inhabit is not an anomaly of the present moment. It is a preview of the ultimate state of the cosmos. The KBC Void is real, its effects are measurable, but several key questions remain unresolved, and they represent the frontier of current research. The most immediate is the exact depth and extent of the void. Measurements from different surveys and different teams have returned density deficits ranging from roughly 10% to 20%. The statistical significance of the void and how seriously it challenges standard cosmology depends heavily on which end of that range is correct. Better galaxy surveys with greater depth and sky coverage will pin down these numbers. Until they do, arguments about the void's statistical rarity rest on somewhat uncertain ground. The causal connection between the void and the Hubble tension remains under scrutiny. The void hypothesis predicts specific patterns in how the locally measured Hubble constant should vary with distance decreasing as measurements extend to larger scales and exit the void's sphere of influence. Recent observations show hints of this trend, but the data are not yet decisive. More precise measurements of the expansion rate at different distance scales will test whether the void is the dominant explanation for the tension or merely a contributing factor. The question of whether the void challenges or violates the cosmological principle also remains open. Homogeneity is expected to hold at scales of several hundred megaparsecs and above. The KBC Void spans roughly 600 megaparsecs, right at the boundary. Whether the principle is violated depends on both the precision of the void's measured properties and on theoretical questions about exactly what scale homogeneity is supposed to manifest. Future surveys will extend three-dimensional galaxy maps to much larger scales, directly testing whether the universe is as smooth as the cosmological principle requires. The modified gravity question remains unresolved. Testing whether gravity deviates from general relativity in void environments requires velocity field measurements with precision not yet achievable. The next generation of surveys will measure how galaxies move in and around voids with much greater accuracy. Any deviations from standard predictions would be a major discovery. The role of the void in the search for dark energy properties is actively developing. Using void expansion rates and shapes to constrain dark energy is a relatively new observational technique. It will mature rapidly as Euclid, DESI, and Vera Rubin deliver their data. Finally, there is the question of whether our cosmological understanding is systematically biased by our location in ways we have not yet fully accounted for. We draw conclusions about the universe from measurements made inside a structure that is almost certainly affecting those measurements. Researchers are developing methods to model and subtract the void's influence from local data, but the modeling requires assumptions about the void's properties that are themselves uncertain. The deeper unsettling possibility is that our location inside the KBC void might introduce biases we have not thought to look for. Every measurement of cosmic expansion, every inference about dark energy, every statistical analysis of large-scale structure made from within the void carries the imprint of our unusual position. Quantifying those imprints, distinguishing what we observe because it is universally true from what we observe because we are standing inside a particular hole in the cosmos, is one of the central challenges of observational cosmology over the coming decade. In 2013, 3 astronomers mapping the universe's matter distribution found a 20% deficit in all directions, an enormous bubble of low-density space with us inside it. That observation, confirmed and refined by subsequent surveys, has grown into one of the most consequential discoveries in contemporary cosmology. The KBC Void connects to the Hubble Tension, one of the most actively debated problems in physics. It strains the cosmological principle, one of the foundational assumptions of modern science. It tests the standard cosmological model at its limits and motivates modifications to fundamental theories of gravity and inflation. It affects our measurements of the universe's expansion history and possibly its age, and it is large enough to sit at the uncomfortable intersection of two unpleasant possibilities. Either we occupy an extraordinarily unusual location in the universe, a position that standard physics suggests should essentially never exist, or the standard physics is missing, something important about how structures form on the largest scales. Neither conclusion is simple. Both are testable, and both represent genuine frontiers of scientific investigation. The next few years will be decisive. New telescopes are mapping the universe at unprecedented scales and resolution. The data they return will either confirm the void's extreme properties and force revisions to our models, or they will reveal that the void is less anomalous than it appears, and that the standard framework is more robust than its critics suggest. Either way, the fact that we are living inside a measurably unusual region of the cosmos is not a minor detail. It shapes what we see, how we measure it, and what we conclude about the universe. The universe is under no obligation to be simple or typical, and our measurement of it is only as reliable as our understanding of the vantage point from which we observe. We are inside a cosmic void. The question is, what that tells us about everything beyond it. Understanding why the KBC void matters requires appreciating how difficult it is to measure the three-dimensional structure of the universe in the first place. The challenge is fundamental. We observe the sky in two dimensions. Every galaxy appears as a point of light in a particular direction, but that position tells us nothing about how far away the galaxy actually is. Two galaxies that appear adjacent in the sky might be separated by hundreds of millions of light years in depth. For most of astronomical history, this limitation was essentially insurmountable. Photographs of the sky showed galaxy distributions in two dimensions, right ascension and declination, the astronomical equivalents of longitude and latitude, but provided no reliable depth information. The cosmic web, with its three-dimensional structure of filaments and voids, was completely invisible. The breakthrough came with systematic redshift surveys. When light from a distant galaxy reaches us, its wavelengths have been stretched by the expansion of space during the journey. A galaxy that is farther away has its light traveling through more expanding space, so it arrives with greater wavelength stretching a larger redshift. By measuring how much a galaxy's light has been redshifted, astronomers can calculate how fast it is receding from us, and from that, roughly how far away it is. The first systematic redshift surveys, in the 1970s and 1980s, were laborious. Each galaxy's spectrum had to be taken individually, requiring hours of telescope time per object. But even with small samples, the three-dimensional structure that emerged was startling. Galaxies were not distributed randomly through space. They formed a web-like network, long chains and sheets, surrounding enormous empty regions. The cosmic void structure became visible for the first time. The 1989 publication of the first CFA redshift survey revealed the Great Wall, a sheet of galaxies spanning 500 million light-years, at the time the largest known structure in the universe. Its discovery forced a revision of theoretical expectations about how large structures could grow. Later, surveys covered progressively larger volumes with larger galaxy samples. The 2DF Galaxy Redshift Survey in the early 2000s mapped about 250,000 galaxies. The Sloan Digital Sky Survey, which began science operations in 2000, ultimately mapped the positions of over 1 million galaxies across a large fraction of the sky, producing the most detailed three-dimensional map of the nearby universe ever created. The maps from these surveys show the cosmic web in stunning detail. Filaments twist and branch, like the channels of a river delta. Voids appear as dark bubbles ranging from tens to hundreds of millions of light-years across. And rich galaxy clusters mark the intersections, where multiple filaments converge. The Sloan Great Wall, identified in the SDSS data, stretches about 1.4 billion light-years, far larger than any previously known structure. The Hercules Corona Borealis Great Wall, identified in a survey of gamma-ray bursts, rather than galaxies, may span as much as 10 billion light-years, though its status as a coherent physical structure is debated. On the emptiness side, the Eridanus supervoid extends about 1.8 billion light-years, with a particularly severe density deficit, comparable to or exceeding the KBC void in some measurements. These discoveries progressively revised upward our understanding of the scales on which structure exists. Each time a new largest known structure was announced, it pushed the limits of what standard cosmology could accommodate. The KBC void fits into this pattern. It represents the largest identified underdense region in our vicinity, and its properties push at the boundaries of what the standard model predicts should exist. Measuring the KBC void required an additional step beyond simple galaxy counting. The void is defined not just by a lower galaxy number density, but by a genuine deficit of matter. and verifying this requires accounting for survey completeness, observational biases, and the possibility that some galaxies are simply too faint to detect. Keenan, Barger, and Cowie addressed these concerns by using multiple independent surveys covering different areas of sky and comparing their counts to theoretical predictions for the expected galaxy density at different distances. The consistent result, a 20% deficit extending to approximately 1 billion light-years in all directions, was robust against these concerns. Subsequent studies using different methodologies have added independent confirmation. Analyses of the peculiar velocity field, the pattern of galaxy motions beyond what cosmic expansion predicts, show the signature expected from a large underdensity. Measurements of the kinematic Sunyaev-Zeldovich effect, which traces the distribution of hot gas in galaxy clusters, show a deficit in our vicinity, consistent with the void's extent. The convergence of independent lines of evidence strengthens the case that the KBC Void is a real physical structure rather than an artifact of one particular survey's selection effects. The KBC Void is only one feature of the complex gravitational landscape that our galaxy navigates. Surrounding the void and influencing our motion through it are some of the most massive structures in the known universe. Understanding these structures illuminates why measuring anything from our location is so complicated. The most famous of these is the Great Attractor. For decades, astronomers noticed that galaxies across a wide region of the local universe, spanning hundreds of millions of light-years, were all moving in roughly the same direction, toward a concentration of mass in the direction of the constellations Centaurus and Norma. This concentration, the Great Attractor, has a mass roughly equivalent to tens of thousands of Milky Ways. The Milky Way itself is moving toward it at around 600 kilometers per second, contributing significantly to our total peculiar velocity. For years, the Great Attractor itself was difficult to study directly. It lies in the zone of avoidance, the band of sky obscured by the dust and stars of our own Milky Way's disk, which blocks observations of more distant objects. Only when X-ray and radio observations penetrated this obscuring veil did the true nature of the attractor become clear. It appears to be concentrated in a region containing the Norma cluster and associated filaments. But the Great Attractor is not the dominant gravitational influence on our motion at larger scales. Behind it, roughly 650 million light-years away, lies the Shapley supercluster, the most massive concentration of matter within about 1 billion light-years. The Shapley supercluster contains dozens of rich galaxy clusters, hundreds of thousands of galaxies, and has a combined mass of roughly 10 quadrillion solar masses. Its gravitational influence extends over hundreds of millions of light-years and significantly affects the bulk flows of matter throughout our region of the universe. The Milky Way is moving toward the Shapley supercluster at a velocity component of roughly 200 to 300 kilometers per second, adding to the effects of the local void outflow and the Great Attractor pull. These contributions partially cancel and partially add, producing our observed peculiar velocity relative to the cosmic microwave background. The Shapley supercluster represents the kind of overdensity that the KBC Void conspicuously lacks. It is a concentration of matter so extreme that it rivals theoretical predictions for the densest structures that should form in our cosmological model. Its existence, at the same time as the KBC Void, a vast underdensity on one side and a massive overdensity on the other, is part of what makes our region of the universe so dynamically interesting and statistically unusual. The Perseus-Pisces supercluster lies in roughly the opposite direction from Shapley, about 230 million light-years away. The Coma cluster, one of the most massive galaxy clusters in the nearby universe, lies about 320 million light-years away. These rich concentrations mark the filamentary wall surrounding the near side of the KBC Void. Mapping how these structures contribute to the local velocity field is crucial for separating the void's effect on Hubble constant measurements from the contributions of individual massive objects. This decomposition requires detailed modeling of the gravitational potential created by all of these structures simultaneously. The most complete models currently available account for masses out to about 300 million light-years and reproduce the bulk flows measured by galaxy surveys at the 70 to 80% level. The residuals, the fraction of observed motions that the models cannot yet explain, indicate that the true gravitational landscape is still not fully mapped. Extended surveys probing masses at greater distances, particularly the region between 300 million and 1 billion light-years, are expected to account for most of the remaining discrepancy. As this mapping improves, the contribution of the KBC Void to our peculiar velocity will be better isolated and quantified, providing a more precise test of whether the void is large enough and deep enough to fully explain the Hubble tension. The KBC Void leaves an imprint not just in galaxy surveys and velocity measurements, but in the oldest light in the universe, the cosmic microwave background. This imprint comes through a physical mechanism called the integrated Sachs-Wolf effect, and it provides a completely independent line of evidence for the void's existence. Light traveling through space gains and loses energy as it passes through variations in the gravitational potential regions of higher or lower density. When a photon enters a gravitational well, a region of higher than average density, it falls in and gains energy. It blue shifts slightly. As it climbs back out, it loses energy. It redshifts. In a static universe, these two effects would exactly cancel, and photons would emerge with the same energy they entered with. But in an expanding universe, dominated by dark energy, the situation differs. While the photon is crossing the gravitational structure, the structure itself is changing. Dark energy causes the gravitational potential of overdense structures to decay over time. Clusters dilute as the universe expands. A photon that enters a gravitational well and then climbs out as that well is shallowing gains more energy than it loses. This effect is very small for individual structures, but cumulative over many. The inverse process applies in voids. A photon entering a void, a region of lower than average density and shallower gravitational potential, exits with slightly less energy than it entered with, because the void has deepened slightly during the transit. The potential well becomes more negative as the void expands and empties further. This leaves a cold imprint on the cosmic microwave background along lines of sight that pass through voids. Astronomers have detected this effect by correlating cosmic microwave background temperature maps with galaxy surveys that identify void and cluster locations. Lines of sight passing through known galaxy clusters show slight temperature excesses. Lines of sight passing through known voids show slight temperature deficits. The correlation is statistically significant and consistent with dark energy domination, which is required for the potential to decay during photon transit. This is an important test of the cosmological constant hypothesis. The integrated Sachs-Wolf effect only occurs in the dark energy-dominated regime. In a matter-dominated universe without dark energy, gravitational potentials would not decay and the effect would vanish. Detecting the effect where it is expected, and with approximately the predicted magnitude, provides direct evidence that dark energy is causing the gravitational potential of structures to evolve. For the KBC Void specifically, its enormous size means that the cold spot it imprints on the cosmic microwave background is potentially measurable, even without cross-correlation with galaxy surveys. Some researchers have examined the cosmic microwave background for a cold region corresponding to the void's location and size. Early analyses found marginal evidence for an extended cold region in the appropriate part of the sky, but the signal is difficult to isolate from the primordial temperature fluctuations present in the CMB from the early universe. This connects to a separate and intriguing anomaly in the cosmic microwave background called the cold spot, a large, significantly colder than average region in the southern hemisphere of the CMB sky, first identified by the WMAP satellite. The cold spot is about 0.1 degrees colder than the average CMB temperature and spans a region of sky roughly 10 degrees across. Various explanations have been proposed, including the possibility that it represents the imprint of a very large supervoid at low redshift. Studies have searched for a corresponding void in galaxy surveys at the location of the cold spot. Some surveys have found evidence for an underdense region, while others have found the underdensity to be insufficient to fully explain the cold spot's temperature deviation through the integrated Sachs-Wolf effect alone. The debate remains unresolved. What is clear is that large voids leave measurable imprints on the oldest light in the universe, providing a cosmological cross-check that bridges observations of the local matter distribution with measurements of the primordial radiation field. One of the most powerful tools in modern cosmology is also one of the most elegant, the use of baryon acoustic oscillations as a cosmic ruler. Understanding how this technique works, and how the KBC Void potentially complicates it, illuminates why our position in the universe matters so much for precision measurements. In the early universe, before atoms had formed, the cosmos was a hot, dense plasma of electrons, protons, and photons. Pressure waves, sound waves propagated through this plasma, driven by the competing forces of radiation pressure pushing outward and gravity pulling inward. These oscillations set up standing waves with a characteristic scale determined by the speed of sound in the plasma and the age of the universe at a particular epoch. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, an event called recombination, occurring about 380,000 years after the Big Bang, photons decoupled from matter and the pressure waves froze. The characteristic scale at which matter clustering was enhanced by these waves was imprinted into the distribution of matter. Today, about 500 million years after recombination, galaxies show a small but statistically detectable preference for being separated by approximately 500 million light-years, the acoustic scale, set by those ancient sound waves. This preference appears as a subtle peak in the statistical clustering of galaxies. The correlation function, or power spectrum of galaxy positions, shows an excess at separations corresponding to the acoustic scale. Because the acoustic scale is set by well-understood physics in the early universe and calibrated against the cosmic microwave background, it serves as a standard ruler, a known physical length that can be used to measure cosmic distances and the expansion history. Baryon acoustic oscillation measurements have become one of the most reliable methods in cosmology, independent of the supernovae distance ladder and the peculiar velocity systematics introduced by the KBC Void. Surveys like BOSS, Baryon Oscillation Spectroscopic Survey, and its successor eBOSS have measured the acoustic scale at multiple redshifts, mapping the expansion history of the universe across billions of years. The current baryon acoustic oscillation measurements are consistent with the lower Hubble constant derived from the cosmic microwave background, around 67 kilometers per second per megaparsec, rather than the higher local value around 73. This is significant because baryon acoustic oscillation measurements are largely immune to the peculiar velocity biases introduced by the void. The acoustic scale is measured at redshifts above about 0.3, corresponding to distances greater than about 4 billion light-years, well outside the KBC Void's influence. This means that two independent large-scale measurements, the cosmic microwave background and baryon acoustic oscillations, agree with each other and both point to the lower Hubble constant, while two local measurements, supernovae and Cepheid distances, agree with each other and both return the higher value. The divide is clean and sits precisely at the boundary of where the KBC Void's influence would be expected to operate. Local measurements within the void return an inflated value. Measurements probing beyond the void scale return the unbiased global value. This coherence is one of the strongest arguments for the void explanation of the Hubble tension. The divide is not random. It follows the expected spatial boundary of the void's gravitational influence. Future surveys like DESI, which will measure baryon acoustic oscillations across a vastly larger survey volume than previous experiments, will sharpen this boundary test and constrain how much of the tension can be attributed to the void versus other possible explanations. Astronomers have developed increasingly sophisticated techniques for mapping the peculiar velocity field, the pattern of galaxy motions beyond what cosmic expansion accounts for, and these maps have become one of the most direct diagnostics of the large-scale matter distribution, including the KBC Void. The principle behind peculiar velocity measurements is straightforward. If we know a galaxy's true distance independently of its redshift, we can compare that distance to the distance implied by its redshift assuming pure Hubble flow. Any discrepancy indicates a peculiar velocity the galaxy is moving faster or slower than expansion alone would produce, driven by local gravity. The challenge lies in measuring distances independently of redshift. Several methods exist, each with its own systematics and precision. The Tully-Fisher relation links the rotational velocity of a spiral galaxy to its intrinsic luminosity. Faster, spinning spirals are intrinsically brighter. By measuring rotational velocity from spectroscopy and comparing the expected luminosity to the observed apparent brightness, astronomers calculate distance. The fundamental plane relation does the same for elliptical galaxies, using the correlation between size, luminosity, and internal velocity dispersion. Using these methods, researchers have mapped peculiar velocities for thousands of galaxies out to distances of several hundred million light-years. The resulting velocity field shows coherent flows, large-scale patterns, where entire regions of space move together in the same direction. These flows trace the underlying matter distribution. Galaxies flow toward mass concentrations and away from underdensities. The maps produced from these surveys show exactly what the KBC Void hypothesis predicts. Galaxies within the void are moving faster than Hubble flow would predict, accelerated outward by the gravitational imbalance. The excess velocity is roughly consistent with the magnitude expected from a void of the KBC's size and depth. Galaxies approaching the void's edge from outside show the velocity reversal expected as matter falls toward the denser filaments surrounding the void. One major peculiar velocity survey, called the Cosmic Flows Program, has measured peculiar velocities for over 30,000 galaxies and constructed three-dimensional maps of the matter distribution derived from these velocities. These maps independently confirm the presence of a large underdensity in our vicinity. They also show the Laniakea supercluster's gravitational basin and the outflow from the local void. The quantitative agreement between peculiar velocity maps and the void density profile derived from galaxy counts is one of the most compelling pieces of evidence that the KBC Void is a physical reality. Two completely different observational approaches, counting galaxies and measuring galaxy motions, give consistent pictures of the same underlying structure. Improving peculiar velocity measurements is a priority for future surveys. The challenge is that current distance indicators, Tully-Fisher and fundamental plane, have uncertainties of 15 to 20% per galaxy, which means measuring the small, systematic velocities introduced by the void requires large statistical samples. Future radio surveys using the 2-1 centimeter line of neutral hydrogen, combined with improved calibration of distance indicators, will reduce these uncertainties and extend peculiar velocity maps to greater depths. One of the more exotic possibilities for explaining the KBC Void's unexpectedly large size involves the properties of neutrinos, nearly massless fundamental particles that were produced in enormous numbers in the early universe, and continue to stream through all of space today. Neutrinos have a strange relationship with structure formation. Unlike cold dark matter particles, which move slowly enough to be gravitationally captured by overdense regions and help build structures from the bottom up, neutrinos move at relativistic speeds, or close to them, given their tiny masses. This means they can escape from small gravitational wells and free stream over large distances without being captured. On scales smaller than their free streaming length, neutrino perturbations are washed out rather than amplified. The mass of neutrinos, though extremely small, with the sum of all three neutrino types constrained to be less than about 0.1, 2 electron volts is cosmologically significant because it determines the free streaming scale. Heavier neutrinos have shorter free streaming lengths and affect structure formation on smaller scales. Lighter neutrinos affect larger scales. In standard cosmology, with massless or very light neutrinos, structure formation proceeds efficiently at all scales above the neutrino free streaming length. In models with heavier neutrinos, still within observational bounds, but toward the upper end, structure formation on intermediate scales would be suppressed. And this suppression could alter the predicted distribution of voids in clusters in ways that might make supervoids like the KBC Void somewhat less improbable. Some hybrid models developed to address the challenges of modified Newtonian dynamics invoke neutrinos as a dark matter component. In these neutrino hot dark matter models, massive neutrinos contribute a fraction of the overall dark matter density. The interplay between the modified gravitational dynamics on large scales and the smoothing effect of neutrinos on intermediate scales can produce a matter-power spectrum that better matches observations of large-scale structure than either standard LCDM or pure MOND can achieve alone. These models remain speculative and contested. The cosmic microwave background is sensitive to the neutrino mass sum and places tight constraints on how much neutrinos can contribute to the dark matter budget. Current CMB data favor very light neutrinos with minimal effect on structure formation, but the constraints are not yet tight enough to definitively rule out small neutrino contributions to the dark matter that might affect the void statistics at the margins. Future measurements of the neutrino mass through laboratory experiments measuring the endpoint of the tritium beta decay spectrum, or through cosmological observations of the neutrino mass signature in the CMB, and large-scale structure will tighten these constraints significantly. If neutrinos are found to have masses near the current upper bounds, it could modestly ease the tension between predicted and observed void statistics. The KBC Void, from one perspective, is simply a large region of space with fewer galaxies than average. That description, technically accurate, misses almost everything important about it. From a cosmological standpoint, it is a testbed for our most fundamental assumptions. It strains the cosmological principle. It challenges the standard model's predictions for structure formation. It provides the most natural explanation for the Hubble tension, one of the most actively debated problems in modern physics. It offers the closest and most detailed laboratory for studying dark energy in a gravity-free environment. And it presents a case study for how our position in the universe influences our perception of it. From a physical standpoint, it illustrates the consequences of living inside a gravitational anomaly. Every expansion rate measurement made locally, every inference about cosmic age derived from local distance indicators, every model of dark energy constrained by nearby supernovae, all of these are conducted from within a region where the matter density is systematically below average, where the gravitational potential is shallower than typical, and where galaxies are moving outward at systematically elevated velocities. These effects are small, individually, but collectively they add up to measurable biases in our most precise cosmological measurements. From a philosophical standpoint, the void confronts us with a question that science has generally tried to move away from. Are we in a special location? The cosmological principle embodies the assumption that we are not. The void creates friction with that assumption, not because we are special in any anthropocentric sense, but because we happen to occupy one of the statistically unusual regions of the universe, an extremely large underdensity whose very existence pushes the limits of what the standard model predicts should occur anywhere in the observable cosmos. Science operates by making measurements and building models that explain those measurements. When the vantage point from which measurements are made is itself unusual, the measurements carry systematic biases that can masquerade as fundamental physics. Recognizing this, characterizing it quantitatively, and correcting for it is the scientific response. The void is not something to fear or to find alarming in any human sense. It is an object of study, a structure of extraordinary scale that reveals the physics of dark energy, the statistics of large-scale structure formation, and the limitations of measuring an entire universe from a single, unusual location within it. What makes the KBC Void genuinely compelling is that it sits at the intersection of multiple open questions simultaneously. Resolving it does not just address one puzzle. It touches the Hubble constant, the age of the universe, the cosmological principle, the nature of dark energy, the behavior of gravity on large scales, and the statistical predictions of inflationary models. Progress on understanding the void is progress on all of these fronts at once. The coming decade of astronomical surveys will deliver the data needed to resolve or sharpen each of these questions. Billions of new galaxy positions, millions of new spectra, thousands of new void maps at different cosmic epochs. This flood of data will force either confirmation of the void's anomalous nature or reveal that our current measurements have understated its size and depth relative to what a more complete sky survey would show. Either outcome leaves us with a clearer picture. Either the universe is stranger and less uniform than we assumed, with supervoids as large as the KBC occurring at rates that challenge our models, or our local neighborhood is indeed a statistical outlier, and we must accept the discomfort of occupying an unusual cosmic address, while still working out what implications that has for everything we think we know. The universe does not owe us a typical location. It does not owe our measurements a clean, unbiased signal. What science can do is identify the biases, quantify them, account for them, and reach understanding that is valid regardless of where the observer happens to stand. That is the work currently underway, and the KBC Void 2 billion light-years of cosmic emptiness surrounding our galaxy is both the reason the work is necessary and the subject it is most urgently needed to explain. To fully appreciate the KBC Void, it helps to think concretely about what being inside it actually means for the observable universe as seen from Earth. When astronomers look outward from our galaxy, they do not see a uniform distribution of other galaxies. They see a structured landscape, clusters, and filaments in some directions, relative emptiness in others. The cosmic web is real and visually apparent in galaxy surveys once you have the depth to map it properly. But from inside the KBC Void, a specific pattern emerges that reflects our position. In every direction, at distances of roughly 500 million to 1.5 billion light-years, there is a shell of relatively higher galaxy density. This is the wall of the void, the filamentary structure that marks the transition between the void's interior and the denser regions of the universe beyond. Surveys at these distances show a concentration of galaxy clusters and superclusters. The Perseus-Pisces supercluster to one side, the Shapley supercluster in another direction, the Horologium Reticulum supercluster toward the south. These massive concentrations form a roughly spherical shell around us, a consequence of sitting inside the void. This observational signature was noticed before the void was formally identified. Astronomers studying the distribution of galaxy clusters at different distances found a statistical excess more clusters than expected at redshifts corresponding to the void's outer boundary. At the time, this excess was attributed to various causes. The void explanation unifies these observations. We see the shell because we are inside it. The interior of the void, between us and that outer shell, is not empty in the everyday sense. Light years of space are not distinguished by their content to any observer who cannot see individual atoms. The void contains dark matter, dark energy, occasional dwarf galaxies, intergalactic gas filaments, and the same physics that governs all space. What is absent is the rich concentration of large galaxies, clusters, and filaments that make up 90% of the mass in the typical filamentary regions. If you could somehow freeze cosmic expansion and travel outward from the Milky Way at the speed of light, here is roughly what you would encounter. For the first 60 million light years, you would pass through the local group and the nearby galaxies of the Virgo cluster region, a familiar, moderately populated environment. Between 60 and 200 million light years, galaxy density drops off from the Virgo cluster's influence, and you enter the more sparsely populated inner void. From 200 million to 500 million light years, you traverse the heart of the underdense region, occasional galaxy groups scattered through relative emptiness, the matter density roughly 20% below the cosmic mean. Beyond 500 million light years, you begin encountering the richer filamentary walls, and by 1 billion light years, you have reached the outer boundary of the void structure and entered more typical cosmic density. That journey from familiar local neighborhood through a billion light years of relative emptiness to the void's outer wall is the scale of the structure we inhabit. For comparison, the distance from our galaxy to the Andromeda galaxy is about 2.5 million light years. The void extends 400 times farther than that in every direction. This scale makes the void essentially permanent on any timescale relevant to human civilization or even the history of life on Earth. The Milky Way is moving outward within the void, but at 600,000 miles per hour, it would take hundreds of millions of years to travel from one side of the void to the other. Meanwhile, the void itself continues expanding due to dark energy, growing faster than our galaxy can move through it. We entered this void billions of years ago, and we will not leave it on any timescale that has meaning for human existence. Mapping the KBC Void and resolving the questions it raises depends on building progressively more complete and precise three-dimensional maps of the galaxy distribution in our region of the universe. This is an observational challenge of considerable scale, and it is one that multiple current and future surveys are specifically designed to address. The fundamental bottleneck has historically been spectroscopic follow-up. Identifying millions of galaxies in photometric images is relatively straightforward. Digital sky surveys can catalog billions of objects from their images alone. But converting that catalog into a three-dimensional map requires measuring the redshift of each galaxy, which means taking a spectrum that shows how much the galaxy's light has been stretched by cosmic expansion. Spectroscopy takes much more telescope time than imaging. For every galaxy image that can be captured in a short exposure, getting a usable spectrum might require minutes to hours of dedicated telescope time on a large instrument. Multi-object spectrographs instruments that can measure spectra for hundreds or thousands of galaxies simultaneously by routing their light through optical fibers to a spectrograph have dramatically increased the bactograph efficiency of redshift surveys. The SDSS pioneered this approach, placing 640 optical fibers on a large focal plane and taking spectra of hundreds of galaxies simultaneously. Its successors have pushed further. The DESI instrument on the Mayall telescope in Arizona positions 5,000 robotic fiber positioners simultaneously, capturing 5,000 spectra in a single exposure. Over its 5-year baseline survey, DESI expects to collect spectra for approximately 40 million galaxies and quasars, mapping the universe's large-scale structure from the local universe out to redshifts above 3.5, corresponding to distances when the universe was less than 2 billion years old. For the KBC Void specifically, what matters most is completeness at relatively low redshifts the region, from roughly 50 million to 1.5 billion light years. Current surveys have reasonable but not complete coverage of this range. Deeper surveys that detect fainter galaxies will improve the completeness of the galaxy census within the void, reducing the uncertainty in how deep the density deficit actually is. The four MOST instrument on the VISTA telescope and the MSE, Mauna Kea Spectroscopic Explorer, being planned for a future large telescope, will extend spectroscopic coverage to fainter objects across large sky areas. The Subaru Prime Focus Spectrograph, PFS, will provide deep spectroscopic surveys over wide fields. Each of these instruments adds coverage that will improve the characterization of the KBC Void and the broader cosmic web in our neighborhood. Photometric redshifts estimates of galaxy distance based on their colors rather than their spectra offer a complementary approach. While less precise than spectroscopic redshifts, they can be measured for far more galaxies with the same telescope time. The Vera Rubin Observatory will generate photometric redshifts for approximately 20 billion galaxies over its decade of operation. For statistical studies of large-scale structure measuring the power spectrum of galaxy clustering, identifying voids in three-dimensional space, measuring the shapes and sizes of the void population, photometric redshifts from surveys of this scale provide extraordinary statistical power, despite their individual imprecision. Euclid combines both approaches. It will take spectra for about 35 million galaxies at high redshift and produce high-quality photometric redshifts for several billion more. Its primary science goals, measuring dark energy and modified gravity through weak gravitational lensing and galaxy clustering, will simultaneously produce a comprehensive map of the large-scale structure around us and at higher redshifts, providing the context needed to understand how typical or atypical our void environment is. The cumulative effect of these surveys over the next decade will be a revolution in our knowledge of the three-dimensional matter distribution across the observable universe. The specific questions about the KBC Void, its exact density profile, its true statistical rarity, its contribution to the Hubble Tension will all be addressed with data far superior to what currently exists. Among the multiple independent lines of evidence for the KBC Void, one of the most physically distinct is provided by the thermal Sunyaev-Zeldovich effect, a mechanism by which galaxy clusters leave imprints on the cosmic microwave background. The cosmic microwave background fills all of space uniformly at a temperature of 2.725 Kelvin. As photons from this ancient radiation field travel through the universe, they can interact with electrons in the hot gas that fills galaxy clusters, the intracluster medium. When a low-energy CMB photon scatters off a hot electron, it gains energy and is shifted to slightly higher frequency. This removes photons from the low-frequency part of the CMB spectrum in the direction of a cluster and adds photons at higher frequencies. The result is a characteristic spectral distortion that appears as a temperature decrement in CMB temperature maps at frequencies below about 217 gigahertz and a temperature increment at higher frequencies. This distortion, predicted by Rashid Sunyaev and Yakov Zeldovich in 1969, is proportional to the integrated thermal pressure of the cluster's hot gas along the line of sight. It is a direct tracer of the hot baryonic content of galaxy clusters, the gas that has been shock heated to tens of millions of Kelvin by the cluster's gravitational potential. CMB surveys like the Atacama Cosmology Telescope, ACT, and the South Pole Telescope, SPT, have used the Sunyaev-Zeldovich effect to detect and catalog thousands of galaxy clusters across the sky. The Planck satellite's All-Sky survey produced a catalog of roughly 2,000 confirmed SZ clusters. These catalogs are largely independent of optical galaxy surveys because they trace the cluster gas rather than the stars. When the distribution of SZ detected clusters is examined in the volume corresponding to the KBC Void, a density deficit is found that is consistent with the galaxy count measurements. Fewer clusters means less hot gas, means a smaller SZ signal per unit volume. The deficit shows up as a statistical underrepresentation of SZ sources within the void's boundaries compared to the numbers expected from cosmological models. This independent confirmation is valuable precisely because it relies on completely different physics. Galaxy counts trace the stellar component of matter-visible stars in galaxies. The SZ effect traces the hot gas in clusters, a component of the baryonic matter that is distinct from stars and is particularly concentrated in the most massive objects. The fact that both tracers show the same deficit strengthens the case that the void represents a genuine shortfall of all matter, not just an artifact of how galaxy formation happened to proceed in this region. Future CMB surveys with higher sensitivity and resolution, including CMB, S4, and the Simons Observatory will detect SZ clusters down to lower masses and at greater distances, substantially improving the catalog completeness within the void volume. Combined with improved galaxy surveys, these catalogs will provide much tighter constraints on the void's density profile. An entirely new observational window on the universe's expansion rate has opened in recent years: gravitational wave astronomy. Since the LIGO detector's first detection of gravitational waves from a merging pair of black holes in 2015, and especially since the 2017 detection of a neutron star merger accompanied by a gamma-ray burst and optical counterpart, gravitational wave observations have offered a new method for measuring the Hubble constant. Neutron star mergers, and potentially black hole neutron star mergers, are standard sirens. Like type Ia supernovae serving as standard candles, neutron star mergers can be used as distance indicators. The amplitude of the gravitational wave signal depends on the intrinsic properties of the merger and on the distance to the source. By analyzing the gravitational waveform, physicists can extract the distance to the merger without any electromagnetic observations. If that distance is combined with a measurement of the host galaxy's redshift, the Hubble constant can be calculated directly. The first such measurement, from the neutron star merger GW170817, returned a Hubble constant of approximately 70 kilometers per second per megaparsec, right between the early universe estimate of 67 and the local ladder estimate of 73, with an uncertainty of about 14%. As more events accumulate, the uncertainty will decrease, and gravitational wave cosmology will independently determine which end of the tension range is more correct. Crucially, gravitational wave sources are at specific distances, and their placement relative to the KBC Void matters. GW170817 occurred in a galaxy about 130 million light-years away squarely within the KBC Void. If the void is inflating local distance measurements, the gravitational wave measurement would also be affected, though in a different way than the supernova distance ladder. Comparing the gravitational wave result with predictions from both the early universe model and the void-corrected local model will provide a new diagnostic. As detectors improve the ongoing upgrades to LIGO and Virgo, and the upcoming LIGO India detector, the event rate will increase to dozens or hundreds of detections per year. With a large sample of events at various distances, the dependence of the apparent Hubble constant on distance will be measurable. The prediction from the void hypothesis is that events within the void should return a systematically higher Hubble constant than events at distances beyond the void's edge. This prediction is directly testable once enough events have been detected across the full range of relevant distances. The future Einstein telescope in Europe and the Cosmic Explorer in the United States will be enormously more sensitive than current detectors, detecting neutron star mergers out to distances of many billions of light years. These instruments will produce catalogs of thousands of standard sirens spanning both the interior of the KBC Void and the more typical density regions beyond it. The resulting Hubble constant measurements as a function of distance will provide one of the most direct tests of whether the void is responsible for the local Hubble tension or whether some other explanation is needed. Science rarely arrives at clean conclusions. More often, discoveries open onto further questions, and the apparent resolution of one problem reveals three more lurking underneath. The KBC Void is a perfect example of this process. A straightforward observation counting galaxies within a billion light-years and finding 20% fewer than expected cascades into questions about the expansion rate of the universe, the age of the cosmos, the nature of dark energy, the validity of the cosmological principle, the behavior of gravity on large scales, and the reliability of every precision measurement in modern cosmology. Each of these questions is individually significant. The void connects them into a single coherent puzzle. The resolution, when it comes, will likely not be dramatic. Science rarely announces itself with clean breaks. More likely, new surveys will gradually refine the void's density profile. The Hubble tension will be pinned down with higher precision at multiple distance scales. The velocity field within and around the void will be mapped with new clarity, and models will be adjusted to accommodate the accumulated evidence. The adjustment may be minor. Perhaps standard cosmology underestimates the frequency of large voids by a factor of 2 or 3, without requiring new physics. Or it may be significant. Perhaps the void requires modified gravity or altered inflationary physics, demanding a genuine revision of the theoretical framework. In either case, the universe will remain strange, and the work will continue. The KBC Void is not an anomaly in the dismissive sense of something that can be wished away. It is a feature of the cosmos, a real, measurable, enormous region of below-average density that surrounds our galaxy in every direction and extends for a billion light-years. Its reality is not in question. Its full implications are. We live in a remarkable time for cosmology. The instruments coming online in this decade are genuinely capable of answering questions that have been unresolvable for the past generation of astronomers. The data that Euclid, DESI, Vera Rubin, and their companion experiments will return over the next 10 years will be transformative. The maps they produce will settle the statistical question of the void's rarity. The expansion rate measurements will resolve or deepen the Hubble tension, The dark energy constraints will narrow the range of possible physical explanations. Our galaxy is inside a bubble of space 2 billion light-years across where matter is measurably scarce. We know this with confidence. What we do not yet know is what that tells us about the universe beyond the bubble, whether the standard framework describes that universe correctly, whether gravity and dark energy behave as we expect on scales we cannot yet map precisely, and whether our current measurements are telling us something about the cosmos, or something about the unusual corner of it we happen to inhabit. Those are the open questions. They will be answered. The void, for all its emptiness, turns out to be one of the most information-rich environments in the observable universe, not despite its emptiness, but because of it.